Welcome to this lecture on the chain rule. In calculus, we often encounter functions that are hidden inside other functions. And today, we will learn exactly how to find their rates of change. This is one of the most powerful tools you will learn in this course. So let us dive right in and build our understanding from the ground up. To begin, let us think about why we need a special rule for these functions. In mathematics, we often deal with composite functions, which are functions placed entirely inside another function, much like a set of nested Russian dolls. The chain rule is our mathematical tool for finding the derivative or rate of change of these nested functions. You can think of it as peeling an onion. We take the derivative of the outer layer first, leave the inside completely untouched, and then multiply by the derivative of the next inner layer. Now that we understand the concept of peeling the onion, let us look at the mathematical formula. The chain rule states that the total rate of change is the product of the individual rates. In Leibniz notation, dy by dx equals dy by du times du by dx. Here, dy by dx is the total derivative. The term dy by du represents the rate of change of the outer layer, and du by dx is the rate of change of the inner layer. If the inner function changes rapidly, it acts as a multiplier, making the overall rate of change much larger. This formula we just saw can be beautifully visualized using a physical system. Imagine three connected gears. The rightmost gear is our input, x, the middle gear is our intermediate variable u, and the leftmost gear is our final output, y. Just as the middle gear transfers and multiplies the rotational speed from the first gear to the last, the intermediate variable transfers the rate of change through the function. If the first gear turns 3 times as fast as the middle, and the middle turns 2 times as fast as the last, the first turns 6 times as fast as the last. We simply multiply the rates. Before we move on to the formal proof, let us see this formula in action with a concrete example. We want to find the derivative of y equals the quantity 3x plus 2 squared. This is an entire expression raised to the second power. To apply the chain rule, we start by isolating the inner layer. We assign the expression inside the parentheses to a temporary variable called u. So, u equals 3x plus 2. By substituting this back, our outer function becomes simply y equals u squared. This crucial step hides the complexity and breaks our problem into two very simple parts. Continuing with our example, we now find the derivatives of these two simple parts. First, we take the derivative of the outer function y with respect to u. Using the standard power rule, the derivative of u squared is simply 2u. Next, we take the derivative of the inner function u with respect to x. The derivative of 3x plus 2 is just the constant 3, since the rate of change of a straight line is its slope. Now, we bring in our chain rule formula and multiply these two individual derivatives together. We substitute 2u for the outer derivative and 3 for the inner derivative. Now we are ready to find our final result. We simplify our expression by multiplying the constants, 2 times 3, which gives us 6u. However, we cannot leave our final answer in terms of a temporary variable. We must replace u back with its original expression, 3x plus 2. Finally, we distribute the outside multiplier of 6 into the parentheses. 6 times 3x is 18x and 6 times 2 is 12. This gives us our final simplified derivative, 18x plus 12. This tells us exactly how fast the original function is changing for any given value of x. Let us solidify our understanding with a second example, this time using a trigonometric function. We need to find the derivative of y equals sine of x squared. Here, the sine wave acts as the outer layer, and the quadratic term x squared is tucked inside. Just like before, we apply the chain rule by setting up an intermediate variable. We assign the inner expression x squared to our variable u. This allows us to rewrite the main function simply as y equals sine of u. We have successfully separated the complex function into two manageable pieces. Moving forward, we take the derivatives of our separated layers. The derivative of our outer function, sine of u, is a standard result, cosine of u. Notice that the inside variable remains completely unchanged at this step. Next, we shift our attention to the inner function, u equals x squared. Using the basic power rule, its derivative is simply 2x. Now we apply the chain rule by multiplying our two separate results together. We multiply the derivative of the outside, cosine of u, by the derivative of the inside, 2x. For the final step, we must remove the temporary variable u from our equation. We replace it with its original value, x squared, to get everything back in terms of our starting variable x. Finally, we rearrange the terms, placing the algebraic part, 2x, in front of the trigonometric part. This is standard practice to avoid any confusion that the 2x might be part of the cosine's angle. Our final answer is 2x times cosine of x squared. We have successfully combined the rates of change into one single mathematical expression. Now that we have used this formula successfully, let us understand where it comes from mathematically. We can build the foundation of the chain rule by looking at small changes. Suppose we have a tiny change in our input variable, which we will call delta x. This will cause a corresponding tiny change in our intermediate variable, delta u, which then causes a tiny change in our final output, delta y. We can set up a simple algebraic equation to link these changes. The ratio of the change in y to the change in x is exactly equal to delta y over delta u multiplied by delta u over delta x. Notice how the delta u terms look like they could cancel out. To complete our derivation, we take the limit of this equation as our tiny change, delta x, approaches 0. In calculus, as these small changes approach 0, the average rates of change become exact instantaneous rates of change, which we call derivatives. The ratio delta y over delta x becomes the derivative dy by dx. The intermediate ratios become dy by du and du by dx. This gives us our final result, proving that the total derivative is indeed the product of the intermediate derivatives. This simple algebraic relationship between small changes is the true heart of the chain rule. So we have proven that the chain rule holds. This brings us to why this rule is arguably the most important rule in all of differential calculus. In the real world, pure and simple functions rarely exist. Everything is interconnected. In physics, if gas pressure depends on temperature and temperature depends on time, the chain rule links these cascading dependencies. In modern technology, it is the absolute foundation of artificial intelligence. When a neural network learns, it uses an algorithm called backpropagation. This is literally just the chain rule applied millions of times to adjust the network's internal weights. Without it, advanced engineering and computer science would grind to a halt. To wrap up our lecture, let us review the key takeaways. The chain rule is your primary mathematical method for finding the derivative of nested functions. Remember the onion analogy? You always take the derivative of the outside function first, leaving the inside completely alone. And then you multiply by the derivative of the inside function. By breaking complex, layered functions into simpler intermediate steps, you can easily calculate how a change in the deepest input ripples outward to affect the final output. Mastering this rule unlocks your ability to analyze almost any complex system in mathematics. Great job following along today.